Welcome to day 8 of our course, and we are getting towards the end. We've covered some exciting topics, and we're going to be covering some exciting topics in today's class as well. I'm really excited in what we're going to be looking at, and I'm more than excited with the topics that we're probably going to complete with. I want to bring in a lot of practicals as we're going to do our troubleshooting. So that at least we can cover as much practical knowledge as possible, because the intention for this course was to be practical as possible. So I trust that you had an amazing day. I had a very busy day. I just finished setting up and getting ready to go online, I think about a minute back. But let us go into our topic for today. So the last lesson, we're looking at managing our networks. We covered things like rack diagrams. We looked at network diagrams, floor plans, how to deal with patch leads. Someone got in touch with me, and that's a very important topic, because if you don't document, you are not going to know the changes that happened in your network, and your network is going to be difficult to manage because you don't have a full picture of the network. So I thought probably in the next class or two, or towards the end, we're going to do just a small amount of time just looking at how do you create a network diagram? How do you document your network? What are the most important things for you to capture so that you can be able to then at least document your own network? I encourage anyone who's working in networking to at least document their own network at work. It might be a small organization, it does not matter. You need to start learning documentation from as small organization as possible, even when you're doing your labs. I will cover this later on, but I'll probably just speak about it just to say, for most people who don't have experience and they have not worked in the industry, and you're wondering, I'm trying to go for a job, I'm trying to apply, but I'm not getting any responses. I would actually encourage you, do a network diagram, document that network diagram, and if you want, attach it to your CV. If not, take it to the day of your interview and be able to put it on the table and walk whoever is taking you through the interview on your network diagram and network documentation, even if it's for a fictitious organization. Just making that effort just demonstrates that not only do you have a desire to learn, but you've taken time to understand the fundamentals. But that's not the focus for the day. I am going to specifically dedicate time to that particular aspect. Our topic for today, we are looking at high availability, right? So we mentioned that in your network, your networks need to be available. Gone are the days when our networks did not carry not so important data. And I'm not saying that our networks have not been so important in the past, but the voice network and the data network were once two separate networks, and most organizations needed more voice than they needed data. So data networks were important, but were not critical. But nowadays, voice and data are now one network. The traffic flows on one network. And thus, when your network stops working, not only are you affecting the data side, but you're also affecting the voice side. And most businesses cannot operate without voice. Most organizations have taken their infrastructure onto the cloud. And for you to access the cloud, you need internet access. So if your network is not redundant, you are not able to meet those particular expectations. So when we're talking about high availability, there are certain key elements that you need to understand. When you go and buy a Google or AWS account, they will tell you about their availability of their data center. And most of the times it is quoted in this value, which is 99.999%. And what this is basically referring to is this is their uptime per year. So this is what they are promising you, that their data center is going to be running 99.999%. If you convert that mathematically, that will give you about 5 minutes. So what they're simply saying to you is that they're guaranteeing you that throughout your entire year, if you host your infrastructure with us, you're only going to have a downtime of 5 minutes. Now that's amazing, because I mean, downtime for 5 minutes, most organizations can tolerate that kind of downtime. On the other end, if the high availability percentage is 99.9999%, What it basically means is that they are talking about a 30-second downtime over 365 days. So you can see that the uptime for most of these data centers is extremely high because there is importance of the data that they're carrying and the systems that need to function. Imagine if Google as a platform was to go down for 5 minutes. I mean, there'd be chaos. Chaos in the fact that you can't watch this video and they can't run ads, and everyone else probably gets affected in the whole process. As I'm sure Facebook has gone down at some particular point. When these outages happen, they are so magnified and all of us get affected in the process. So the data centers are basically thriving that from their end, they'll give you capacity, power, data connectivity, 99.999%. So it is important for you to have an understanding of what is the high availability terms that are used when you're dealing with these data centers. Now, the next important value that you need to understand is what is known as the mean time to repair. And the mean time to repair is basically measuring the time it takes to fix a failed component. So if we're looking at it from a time perspective, I'm just going to try and draw this. So 0, 2, 4, these are hours, 6, 8. So if a failure happened at this point and the repair of the component that is failed happens, at 6 p.m., then it took 4 hours. So the mean time is calculated as 4 hours. And this value is very important because when you're dealing with something known as SLA or a service level agreement, all these values are agreed upon when you're signing the contract, so that when something goes wrong, you know that according to your SLA, the issue must be resolved in 4 hours' time. So you then take that information to the business, and the business will then be able to tell you that they can accept that risk. If they can't accept that risk, they'll probably tell you that they want a much better guarantee, meaning the time to repair must be smaller than 4 hours. It must come down to be at least 30 minutes. Now, if your time to repair becomes 30 minutes, then it basically means that the components that are likely going to fail cannot be sitting in a warehouse somewhere. They have to be stored on site so that in the event of an issue, then you can be able to get the failed component, swap it with something else. Those that have dealt with Cisco is what they call 4-hour turnaround time. So if you have a 6500 switch, which is probably one of the very big production switches, and you lost one of the modules on that particular switch, depending on the SLA that you have with Cisco, in 4 hours, they would have sent a technician on site to deliver the failed component. So mean time to repair is just focusing on the time it takes between the failure and replacing the component. Now, the mean time between failures is the average time between system breakdowns. And this I'm going to take a step back, because the mean time between failures is trying to calculate over a period of time. So let us look at this over a 12-month period. Let's see, over 1,000 hours, 1,000 hours. And for some reason, our equipment fails 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. So in that period of 1,000 hours, our infrastructure failed 8 times. So the mathematical formula would be 1,000 divided by 8, which will give you 125. So 125 is kind of the average time between failures. So you're assuming that every 125 hours, I need to anticipate a failure in this equipment. And if that's going to happen, how then do I mitigate, or how do I then protect? So in simplicity, if I was to break this down, I want you to think of the tires of a car, right? The tires of a car, when they're brand new, maybe they can give you, let's say, 100,000 kilometers. After 100,000 kilometers, there is assumed perspective that the tires will be worn off and they need to be replaced. So over 1 million kilometers, you're probably going to replace your tires 10 times. So when you get to the 99,000 kilometer mark, you need to be prepared that the tires are going to be worn out, and thus either we're going to do a replacement of the tires before the failure happens so that we can then be able to mitigate that from transpiring. So that is calculated as the mean time between failures. The next value is the recovery time objective, which is known as RTO. And RTO, see a pen. I just want to make sure that I've got a blue. All right, let's see. All right, I've got a yellow one. I just wanted to make sure that I've got different colors so that we can be able to draw and make it clear. So RTO is the maximum time to restore critical functions following a disruptive event. So RTO and mean time to repair almost similar. So if an outage happened at this point and we repair it at this point, it means between here, there are 6 hours. So the recovery time objective, and this, once again, is agreed by the business when the system comes live. And then when you're drafting your SLAs, you are then saying to yourself, this is the minimum amount of time that the business can tolerate. And when you as a provider sign that SLA, you are simply saying that we will be able to restore any outage that might happen in regards to this device or system in 6 hours. Then the other one is the RPO, which basically describes the period of time in which the enterprise operation must be restored following a disruptive event. Now, I'm going to take a bit of time to explain this because it's not as clear from the very onset. So let us assume that this is 12 midnight, so 00 in the morning. This is 6 a.m. This is 12 noon, and this is 6 p.m. And our databases are backed up at 12 midnight. And then a failure happens at 7 a.m. Between 12 midnight and 7 a.m., our data was not being backed up because our backups ran at what? At 12 midnight. And that is what is being described as the RPO, which is the period of time in which an enterprise operations must be restored following the disruptive event. And this is the time elapsed since the most reliable backup. So in this case, there's a very high chance if your backups were running at 12 midnight and an incident happened at 7 a.m., there was no backup that happened between that time, and there's a very high chance that you basically lost all the transactions that happened between 12 midnight and 7 in the morning. Now, for a banking system, this is not acceptable because imagine you did your transfers at 8 a.m. in the morning, and then the bank says, oh, by the way, we did not save that information, and thus we are going to act as if that transaction never happened. I mean, banks trade a lot of money, so with most banking infrastructure, they'll probably be running snapshots. I would want to assume, every few odd minutes, and they'll probably be backing information in real time so that in the event that anything happens, they've got the capacity to be able to then restore and bring the services online. So when you're dealing with high availability, it is important for you to understand these terms because these are the terms that are going to determine what do you need. And as you can imagine, the more you record information on a more real-time basis, it means that your storage is going to be very big because now you are storing so much data. And also your recovery must be so quick enough that when something goes wrong, you're then able to restore. You can't be storing data in one location. So your data has to be distributed so that if an incident happens, imagine Barclays Bank or Standard Chartered Bank having all their infrastructure in one location. And if something went wrong with that one location, means all the transactions are lost. So they have to then redistribute their information into multiple areas just so that they can be sure that an outage in one location does not cause an outage in all entire systems. And with all the efforts that we might take, sometimes outages will still happen, but these are some of the key points that help us to communicate what the business needs and what it is that we can be able to do to be able to then remedy everything that is taking place. So I trust, this is making sense. If you've got any questions, you know what to do. You can just send your questions. I'll be able to answer them, and then we can then go forward. The last two is the recovery point objective. I think I spoke about that. The last one is the service level agreement. And this is an agreement between a service provider and, okay, good. This is an agreement between a service provider and a client, which basically identifies the responsibilities, right? Who is responsible for what? It also looks at availability. What are the agreed availabilities? It also looks at responses. So for those that have worked in the industry, or those that have seen people working in the industry, you find that IT people are on something known as on-call, which means that 24/7 support. You might get a call at 3 o'clock in the morning when systems have gone down, so that you can be able to what? To remedy them. Why? Because the service level agreement says in the event of an outage, we're expecting services will have a technician or an engineer on site in less than 30 minutes. So when you're on call, you can't drink, you can't go to the club, you're just going to be sitting waiting for your phone to ring because there might be an outage at work and you might be required to then come and fix it. And what drives that is things like service level agreements, which basically define who's responsible, what is going to be available, and who's going to respond in what particular time. And that takes us to the redundancy options that we have on our network. So we've got layer 2 redundancy, and layer 2 redundancy basically looks at our switching infrastructure. And we say that we have switches on our network. Right, so this is our switch, this is our switch. A single point of failure is when we have one switch that is connecting 200 devices, or sorry, maybe not 200 devices, let's say 40 users are hanging off one switch. And if that switch was to go down, it basically means that no one can reach the internet because the switch has gone down. So this path has gone down, this path has gone down. And that's something that we call a single point of failure. If one thing was to go down, then everything else would then be able to what? To go down. And I'm sure we deal with single point of failures in everything that we deal with in life. I want you to imagine an aeroplane with one engine. Would you fly on that aeroplane? I would assume not. If the captain was like, ladies and gentlemen, welcome aboard to our flight. Oh, by the way, we only have one engine for this flight. I'll be like, okay, take me down. I'm not going. Why? Because if the primary engine failed, you don't have any backup option. So planes usually have two engines. Planes usually have two pilots, so that in the event of something happening to one pilot, another pilot can be able to take over and fly the aeroplane. And I'm sure you've heard stories where a pilot fainted or collapsed and another pilot had to take over. Imagine now if the plane had one pilot. That would probably be disastrous and catastrophic. So we need redundancy. And in our networks, we've got two levels of redundancy. You've got layer 3 redundancy, we've got layer 2 redundancy. Now, layer 2, we are talking about the switch. That's layer 2. So what options do we have? We need to build a network that is distributed. That's the starting point. We need a network that has multiple points. So I'm just going to erase this and probably draw what would be a network with redundancy, right? So you've got two options. You can either have two switches, 20 people connected here, 20 connected here, and then you've got a path going this way, and then you've got your uplinks on the other end, and then you've got these interconnected. So if anything went wrong, people can go this way or they can go that way, right? So you have eliminated single point of failure. You got multiple points. Yes, Brett, thank you very much for your comment. Let me see, let me just come back to it. Just scroll that through, let me show it. All right, so let me come back one step. All right, so we need to build networks that have no single point of failure. So this is one design. The other option is you can stack. Let me just make sure I've got my pen. I need a different color. Okay, right. So you can stack your switches and they are connected using a stack cable. So ultimately, if one switch was to go down, the other ports are not affected, or you can just migrate the ports to the bottom switch and you got everything else connected. So we need to avoid single point of failures on our network. Now, you can run you can run a distributed network and do it the way that I've just given as an example. But when you're talking about the high spec switches like the 6500, you have something known as a supervisor engine. So you got two switches, and then they've got a supervisor engine that controls the switch, and then they will have dual power supplies that are bringing power to the switch. So in the event that any of these fail, the other is able to take over. And not only that, they use a technology known as virtual switching, which basically combines these two switches to make them look like one. So to the downstream devices, they are seeing one switch, but behind that, there are two individual switches. So if one switch was to go down, the other will take over. And that is known as hardware redundancy on the layer 2 technology. The switches run in a mode that is known as active standby. So one switch is active, the other one is what? Standby, just waiting that in the event of a failure, it then picks up and then continues running. So redundancy is very important. On a switch level, you got active standby, or you can use stackwise. And stackwise, I will explain it once again. Unfortunately, I don't have a switch that I can probably demonstrate. But with stackwise, you have one switch, two switches, three switches that are standing as individual switches, each with about 24 ports. And then you've got a stackwise cable that connects the switches, and this makes a switch look like one switch. So from a connectivity perspective, it will be one switch with 3 layers. And if one switch was to go down, the other two can be able to then continue forwarding, and then you can have your uplinks going through. So redundancy is something very, 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 very important, because if you don't plan with redundancy, then you're going to have issues, because any failure that's going to happen on your network is going to wake you up at night. I think one of my greatest joys with redundancy is the fact that I can sleep peacefully as a network engineer, knowing that if one device was to fail, I'll get to the office the following morning, I'll figure it out, and then I'll be able to replace it. I'm not going to be running around at 3 o'clock in the morning because everything else has gone down. So try and plan your networks with redundancy in mind. But you don't only implement redundancy at layer 2 switch level. You can be able to implement redundancy on the server side. And you've heard something known as NIC teaming. So this is when you got a server, and then on that server, you got 2 network cards. And then you run these 2 network cards onto your switch, and then you bundle them into one network card. So when the server sees that network card, it sees one network card. When you configure IP addressing, you're configuring IP addresses on one network card. The 2 are in what is known as a NIC team, or in some terms, they call it a cluster. Right, so you're clustering your network interface cards so that if one interface card was to go down, the other one will continue passing traffic. And this is very crucial when you're dealing with servers that are hosting information that is very important. So when you're doing NIC teaming, you've got 2 options. You can either have active-active, and active-active means that your data is flowing on both links at any given time. So both links are live, and active-passive means that you're running one at any given time. So redundancy, very, 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 very important. And when I think of redundancy, I just think of basic things. When you drive a car, you're always going to carry a spare wheel. Why? Because if anything happens, you need to be able to then what? If you had a flat tire, you need to have a spare wheel for you to be able to change that and then continue moving. If you move without that, then you have a problem. But at the same time, not everything can be made redundant. I said to you the last time, you can't drive with a spare engine. It's just not practical for 2 reasons. If you had a breakdown, you can't take off the engine and change it by yourself anyway. So what's the point of carrying it? And if you come from Africa, and my African brothers, you know that, sometimes when I came, my country had issues with petrol at some particular point in time, and you had to drive with an additional 20 liters of petrol in the car, so that if you run out of fuel and you can't find fuel at the service station, you can just pour in. So there are things that you can implement redundancy on, and there are things that you can't be able to implement. So let us look at the layer 3 side of redundancy. What options do we have and how best can we implement? Now on layer 3, we spoke about this the last time, about the hot standby routing protocol, which is known as Hsrp in short. And Hsrp is a gateway redundancy protocol. And I'm just going to draw our distribution switches. So this is our distribution layer, and this is our access layer. And then we have this interconnected, and this goes to the cloud, which takes us to the internet. And then and then this way, we've got our access switches, which every other user is connecting to. And we said the last time that you've got a PC that is sitting here. When you configure that PC with the default gateway, this is the IP address that you would give the PC, right? So you give the PC an IP address that is sitting here, default gateway 192.168.1.1. That's your default gateway. Fantastic. What happens if this switch goes down? In a normal scenario, you basically lost your default gateway. So Hsrp then comes into play and says, okay, instead of allocating your gateway on this device or on this device, I am going to come up with a virtual IP, right? That is going to be serviced by these two devices. And then I'm going to allocate 192.168.1.3 as the default gateway. And it is being serviced by these two switches. So if this switch was to go down, this one will then service the requests that are related to that gateway. So all it's basically doing is just providing gateway redundancy. I hope that makes sense. If you want to look at an example, you go to the airport, right? This is the airport. This is where the airplanes are, right? So the airplanes are waiting at the tarmac. You got multiple gates to get to the runway so that you can catch the airplanes. If this gate was to go down, you could be able to use gate number 5. If gate number 5 had an issue, you can go to gate number 10. Now imagine if the entire airport had one gate, and for whatever reason, that gate is not working. It means no one else can go out of the airport. And this is the typical case in point where Hsrp basically then says, I'm going to function and provide a virtual IP address and also provide you with a virtual MAC address. So you get a virtual IP and you also get a virtual MAC address that is then distributed in the back end. It will then handle the two. Hsrp is a Cisco proprietary protocol. So the vendor neutral option of that is known as VVRP. It works just like Hsrp, but it can work on non-Cisco devices. When Hsrp works, it is active and standby, meaning that there's only one router or switch that can be the active switch at any given time. When it goes down, the other one then kicks in. VVRP also does the same thing. It's an active standby, but it is multi-vendor. It's a multi-vendor solution. And then GLBP is Cisco proprietary, but it can then load balance between multiple switches. So if this is on my router, 1, 2, 3, with GLBP, all of them are active at the same time. So some people will be sent to this one, some people will be sent to this one, other people will be sent to that one. So at any given time, all three of them are live. But with Hsrp, it is active standby. So that's what you need to understand. Active standby, and this one is active. So it can load balance across multiple switches and traffic can be able to flow at any given time. So this is redundancy from a layer 3 perspective. So now we have dealt with this. These are also known as first hop redundancy protocols. So if you come across someone else or another textbook that says first hop redundancy protocol, this is what they're referring to, because it's your first hop from your PC going to your default gateway. And then the last time we spoke about LACP. So now we have dealt with gateway redundancy. What other redundancy options are available? And we said we have our switch. When we connect one cable, the dilemma with one cable is that if the cable breaks, then these two switches can no longer talk to each other. And that creates an outage. However, if we add more cables, we also spoke about spanning tree. And we said spanning tree is a loop prevention protocol and spanning tree is going to block all these other ports and only leave one port running and live. So they came up with a technology known as LACP. And what LACP basically does is it then basically bundles all these interfaces into one logical interface. So because it's now one logical interface, spanning tree is not going to block because it's only seeing one logical interface. And because these are 4 gig links, that pipe becomes a 4 gig pipe. So if one of them was to go down, the other three will continue forwarding. And yesterday we had an incident at work. And this is just to demonstrate the practicality of this. We had a user who was downloading traffic. And they were using almost a gig of bandwidth, downloading whatever they were downloading. And if we only had one link between the two switches, it means that that user could have consumed all the bandwidth for everyone else. But because we had LACP link aggregation running between the switches, it meant that we had more capacity because we had more cables that were running between the two switches, allowing us to be able to then handle this particular issue. So this is a practical example of how these technologies can then be able to save you at some point in your network, because LACP allows for multiple channels to then become one particular channel. So it is known as Link Aggregation Control Protocol. The Cisco version is known as PAGP, but in Network Plus, you don't focus on that. You focus on LACP because it is the vendor neutral alternative. Now, it will be pointless for us to do all these things when we don't have redundancy in terms of power, because at some point you're going to have a power outage. Doesn't matter which country you stay in, you will have a power outage at some particular point. It's not an African thing. Yes, I know we have more power outages in Africa, but yeah, I'm here in Australia. We do encounter power outages. Actually, we had a critical incident about a month and a half back that was power related. So we all know UPS devices. UPS devices give us uninterrupted power supply. But before I go ahead and focus today, I'm so excited. I don't know, I just feel energetic. I'm just gonna look at the chat and see if there are any comments, any questions, and then we can be able to proceed. So if you've got any questions, please just drop them off in the chat and I can attend to them. Right, let's see. All right, so is Nick, let me just put that on the screen. Is Nick Tim the same as Nick Trunking? I'm also sure about Nick Trunking. Let me just double check on my phone and just make sure that I am giving you the correct answer. Let me see, Nick Trunking. Okay, yeah, so from what I'm gathering, Nick Trunking and Nick Timming seem to be one and the same thing, Brett. I guess the objective that we're basically trying to achieve in either of these two scenarios is the fact that we have a server with multiple network interface cards, and we are basically connecting these to a switch, going into multiple ports on a switch, and then we are then bundling this to appear as one network interface card to the outside world. So the terminology might be different. Nick Timming, Nick Trunking, the objective that you're trying to achieve is basically the same objective. All right, so then let's go to the next question. I'll make sure that I'll put it on the screen. So is that two switches seen as one with 4 power supplies? That is correct. So you are referring to the time when I was talking about, let's see, I need to, okay, erase, cool. So you are referring to the time when I was talking about the supervisor. So you'll have your supervisor, you'll have your dual power supplies, and you've got a dual power supplies, and then you got your network ports, and then using the virtual switching technology, this is then using something known as VSS. This is then presented as one switch to the rest of the network. So when I'm connecting my distribution switches to my core switch, I'm going to have a cable going this way. I'm going to have a cable going this way. It might look like I'm going to one switch, but behind there are two individual switches. And if one of these switches was to go down altogether, the other one takes over and they run in an active standby mode. So the one is active, other one is standby supervisor engine. The ports will be functional. Supervisor is the brain of the switch. So when the primary one fails, the other one continues, and they use a technology known as stateful switchover. And with stateful switchover, it basically means that when the primary is running, the secondary is capturing everything. So it's got the MAC addresses, it's got everything that's happening. So when a failover takes place, it just automatically switches and then crosses over. So it's like running a car with two fuel, with two petrol tanks. When one tank finishes, the other one kicks in without, same thing with an airplane, right? When the fuel finishes on one side, it just crosses over, hoping that you don't get to that point. But I guess you're probably getting my point on what I'm just trying to say. So I hope that is answered. Let us continue. I'll come back to the UPS scenario just in a second. All right, so if you've got any questions, guys, just let me know in the comments. I'll answer your question and we can be able to then go through. All right, so just come back one step backwards. Okay, so now we're talking about UPS, which is uninterrupted power supply. We all have UPSs. So what a UPS basically does is it's got a battery. So you've got a battery that is sitting, and then you've got your infrastructure sitting in front. And then the UPS is connected to the power source. If you lost this power source, this battery then provides power to your devices. And sometimes they can go for 4 hours. Sometimes they can go for 30 minutes just to allow you to then restart. The one critical thing that UPSs do for you is they protect you from brownouts. And brownouts is when there is a drop in power, but not a blackout. But sometimes that drop in power causes the devices to restart. And one thing that you don't want to restart on your network unplanned is things like storage. Because you might interrupt a backup that is taking place and all of a sudden you lose power, devices restart, the backup was at 90% and then bang, that backup fails and you're back to square one. So redundancy for power is very important. It's one of the cheapest things to probably try and remedy anyway. And now let us look at backups. So what type of backups do you have? We've got the full backup, and by the name full backup, it's very clear and straightforward. We are backing up everything that is sitting on that particular server. But you can't do full backups on a daily basis. Why? Because if you're backing up 4 terabytes of data per day, over 30 days, you're probably looking at 120 terabytes of data. And maybe that backup is going to take 8 hours because it's backing up all the information. So you can't back up all the data every day. So you do full backup, and there's something known as an incremental backup. And the incremental backup just focuses on what changed. So if this data was the same and only this part changed, incremental backup is just going to back up this top part. Why? Because that's the data that basically changed. It will leave everything else as the same. However, because you're backing up what changed, you can't restore incremental backups without a full backup. So you need to restore the incrementals on Thursday, on Wednesday, on Tuesday, on Monday, before you can get to the Sunday full backup. So when you're restoring, it's longer to restore incremental backups, but it's faster to back up because you're only backing up what changed. And then differential starts with the full backup, and then it increments the data that is basically changed. So the good thing with the differential backup is in itself, it contains the full backup. However, it is just going to then do incrementals. So when it's doing a restore, it's coming from the incrementals going back to the full backup. So it's got everything that you basically need. So you can restore from that. So when you're working out your backup strategy, be mindful of the time it will take to backup versus the storage capacity versus the restore times that the business will require for you to be able to restore in the event of an outage. And the most exciting one that has come through as a result of virtual environments is something known as a snapshot. And a snapshot is a point of truth at any given time of a system. So right now, I'm talking to you. If I were to snapshot my PC, it means that it's going to get a timing moment of my PC right now. And if anything was to happen, I can be able to restore back to that particular point. So snapshots have become a savior, especially in a virtual environment, because before you make any changes to a server, you can just do a snapshot of it, and then you can restore the snapshot if anything goes wrong. Right? I'm sure if you've got Windows 10, at some point you've seen these snapshots being taken and them happening. All right, let's just try and see. I think I see a question. All right, so would you need a, all right, let me just put that on the screen so that everyone else can see. So would you need to cable port to port to enable failover to work? I would imagine if a client PC is plugged into one switch that goes down, how does the network reroute? Okay, so from a switch perspective, if it's a client PC, you can't obviously connect a client PC to two different ports because the PC can only go in one direction. So this is your PC, this is your switch. Right, the PC can only go this way, and there's no other path. So if anything happened to this switch, then you're going to lose connectivity. That is correct. However, if your switches were stacked, it means that if this switch went down, but this one is still running, I can just go into the server room and move this cable onto the switch on top. And then all of a sudden you're back online. So from a physical standpoint, if anything happened at this level, then yes, I can just move this and then you can continue working. Because they're running as one and the same device, it's easy for me to do compared to me trying to replace the switch, taking away all the cables, plugging it in, putting all the cables, doing all the configurations and bringing the switch system online. It might take longer, but with the stack, it can be quicker. So what you're aiming with redundancy is what's the quickest way that I can restore services in the event of an outage. And this is what StackWise and other technologies will be able to then help you to be able to then do. So yes, you're correct. You can't run two cables. So you're going to have some form of outage at some particular point, but you're going to restore it much more quicker and get that going. But if it's a server, then you're going to be running two different cables going in two different directions. So if one was to go, so usually when you're doing NIC teaming, this will go to the switch on top. So if you lost one of the switches, you still have connectivity. So that's your redundancy in that perspective. All right, so let us see what, okay. So that is high availability. Now we're looking at security. We are looking at network security. How do we secure our networks? What are the components that are required in order for us to secure our networks? And when you're dealing with security, there is what they call the security triad. Triad as triangle, as three sides. And the triad is basically looking at when you're protecting infrastructure, there is the confidentiality aspect, there is the availability aspect, and then there's the integrity aspect. So when you're dealing with confidentiality is how do you protect the information? How do you make sure that no one has accessed that particular information? And then when you're transporting that, how do you protect it in transit when it gets to its particular location? And the simplest that I can think of is the guys who move money. You know, the guys who carry the money trucks, the one that take money to the bank. They come and get money from your shop. They protect that money during transit until it gets to the bank, and then they then offload. And there has to be a mechanism that verifies that the money that they took from the shop is the money that arrived at the bank. Because I can say to you, maybe I deposited 500,000, but they might get to the bank and say, no, we only have 450. How do we confirm that 500,000 is what left and 500,000 is what made it there? And one of the ways that they do it is the trunks that they carry the money in cannot be opened by the security guys. They can only be opened by the person who's sitting where? At the bank. Maybe the guy at the bank is the one who's got the key. So this is my example. So you got a trunk here. When I put the money inside, I lock it. My padlock is very terrible. You drive with the money, you get to the bank, and then someone at the bank has got the key to the padlock. They open it, and then they count the money. If this key was not tampered with or broken, the assumption is if I counted 500,000 here, 500,000 is supposed to come out on the other end. If this key has been tampered with and the money is no longer 500,000, even if it's 500,000, if the key is tampered with, it basically then confirms that somewhere along the lines during transit, someone tampered with the contents. And thus, I need to then verify if, number one, the money that is in there is genuine or not, because someone might have replaced the notes that I put with fake notes. So why does this matter when we are looking at network security? Confidentiality ensures that the information is protected from unauthorized access or disclosure. This means restricting access to that particular information. But how do you protect it? So there are multiple ways to protect it. You can protect the data by using firewalls. Right, so with firewalls, I'm trying to protect access to the data so that people who don't have access to the data can't get into the organization to access it. So you got the firewalls that are protecting the data. You can use credentials when you're accessing systems, username and password. What are you trying to do? You're trying to protect the data that is sitting behind on the other side so that only someone with the right credentials has the ability to then access that particular data. And as traffic is flowing through, you can't let traffic flow in clear text. Imagine you're doing a transaction and you log into the bank at home on your PC. This is your PC. This is your bank. You connect via the internet, which is not very secure. And then you send your username as plain text. So my username is John. My password is Cisco123. And all this is in plain text. If someone was to sit in the middle and snoop on that traffic, they can get the username and password, they can then log in, and then they can withdraw money. So as the traffic is traversing through, we need a way of encrypting that data so that it is protected. And in the next slide, we're going to look at encryption, what it is, how does it work, and what are the different types of encryption algorithms that are available that can then help us protect the data. Now, going back to our money truck example, most of the trucks that transport money nowadays, in their cases, they've got some ink that if someone was to violently open the safe, that ink basically spills out and it taints the money. In one essence, they're basically simply saying that they're trying to make the money unusable so that anyone who then goes to the bank with money that is purple and pink, whatever color it might be, it's easily identifiable that this is the money that was what? That was stolen. So going into encryption, just go to the next slide. So the process of encryption is taking plain text like this one, passing it through an algorithm, and then getting your gibberish being spewed out on the other end. And then you transport this over the internet. So if someone wants to intercept, they can't decode this. Why? Because when encryption happens, there are keys that are involved to lock and to unlock. And that basically leads us to the two types of encryption systems that you find in the security industry. You got the symmetric encryption, which means that the key that locks is the same key that unlocks. Symmetry. One side is equal to the other. So the key that locks in symmetrical encryption is the one that unlocks. And as you can imagine, the key that locks the money when the guy is collecting the money from the office, and the key that unlocks at the bank is the same key. Whilst that is secure, there's a risk that if someone was to get hold of one key, then they've got access to the whole platform. Asymmetric encryption is when you got two keys that are different. So these keys work in pairs, meaning the one that locks is not the one that unlocks. The one that unlocks is the totally separate key. So you have to then steal both keys in order for you to then gain access. And that is going to be much of a challenge. So asymmetric encryption algorithms are much better security-wise, but they're also intensive in terms of processing. So we're going to look at when do we use symmetric and when do we use asymmetric encryption keys. So what are the three types of encryption keys? So encryption protocols or algorithms that you find. You got DES. DES has now been done away with in the industry because it could be manipulated. And the reason why DES could be manipulated was the number or the bits of the key or the key size, right? They call it the key size. And I think the size for DES was 56 bits. And I want you to think of 56 bits as, let's look at a key. And let's say this key is this long, right? Let me see if I can make it shorter. Might have to erase everything to get that done. Okay, we'll draw it again. So this is our key. And this is how short our key is. Right. The pattern of the key, because the key is short, it means that it's easy for someone to kind of duplicate this key and try and recreate it. A DES key was a 56-bit key. And I want you to think of a bit in terms of 2 to the power x, where x is the size of the key. So 2 to the power 56 could give us so many permutations. So then if you brute forced and you're the machine that could compute all these numbers and try all the combinations, then that key could then be broken. So the challenge with DES was the fact that the key size was small and there were supercomputers that can then compute enough combinations to then break that encryption. DES was superseded by triple DES. And as you can see, the name triple DES is just a multiplying effect of the key, increasing the key size to 168 bits. And that too has basically been compromised. There are computers that have been able to break the triple DES key. So now the preferred is AES, known as Advanced Encryption Standard. And AES uses up to 256 bits. So the key size is up to 256 bits. So 2 to the power 256, I can't even imagine what the number is. And right now the challenge is there are no computers in the world that have the capacity to come up with so many combinations in a reasonable amount of time. Right, so you are chasing a numbers game, as at some point someone is going to then get a super computer that has the ability to be able to break some of these algorithms. And when that happens, it's going to break a lot of things. But for now, this is what's still functional. So these are the three most common symmetric algorithms that you find in the industry in as much as security is concerned. Now we looked at encryption. Now we need to look at data integrity. Remember, our triangle was confidentiality, integrity, and availability. Now, integrity basically looks at what has been sent. Is that accurate? So when you look at integrity from a day-to-day conversation, there are people that you trust and there are people that you don't trust. There are people that if they gave you information, you're going to trust that information. Why? Because they are people of what? Integrity. And integrity in the security space or in the networking world or in the IT world is whatever I receive is that the true copy of what it was at source, right? So if someone was to write a letter and in the letter they write whatever they write, maybe they say, give Tinei $500, right? And then they send this letter with someone carrying. How do I know that when the letter comes here, this information is still accurate? So in security, we use something known as hashing. So what hashing basically does is that when the information is generated as source, you run it through a hashing algorithm or a hash function. And that hash function spews a particular number, right? And then that number is attached to the information that you're sending. The person on the other side, when they take that same file and run it through the hash function on their end, they're supposed to come back to the same value. And if the values are identical, then you can then be sure that the data has not been compromised or manipulated in the process. And the typical case in point is when you are dealing with Cisco infrastructure and you want to download iOS images. When you go to the Cisco website, they'll give you a SHA hash of the image that you're downloading. When you download the image, before you run it on your infrastructure, you can then run that same file through a hashing function and then compare the hash that you got from Cisco with the hash that you got on your end. If the hashes are identical, that then confirms that the data has not been tampered with. Now, hashing by itself, whilst it is good, it cannot fully protect because it can be what? Manipulated. Because the game with hashing is, let's take, for example, this file had 90 characters. And then I manipulated the information in the process. But I made sure that the new file that I created also had 90 characters. When the hash gets run, there's a very, very high chance the hash value would be the same. So in order to protect against that, they came up with a HMAC, which used an additional key on top of the hashed function to protect so that you can't reverse the hash. So hashes by nature are one way, right? You can't, the mathematical formula for hashes is one that when you hash going forward, you can't hash backwards. That's the mathematical formula, but we're not going to cover that. If you do algorithms and detailed cryptography, you then look at the actual mathematical formula that then does this whole hashing process, and it was designed in a way that it's one way and you can't do it backwards. And the other thing with hashing is when the file gets manipulated just a small bit, the whole hash changes drastically. So you can't, it's not an incremental like 99, 100, no. The whole hash changes. And then the third aspect about hashing is that it has a fixed key size. So the hash size is fixed. If it's 128 bits, it's 128 bits. It doesn't matter the size of the file. The hash size is always going to be the same. So the two most common integrity protocols or algorithms are MD5. Let me just put that in yellow. MD5 and SHA. Those are the two most common hashing algorithms that you basically find. MD5 has been compromised, so it's not recommended. SHA is the most preferred in the industry as of today. I will check once again if there are any questions, and we can then be able to proceed. Probably give myself a time to just sip in a bit of water and get going. Let's see. All right, looks like there are no questions. I'm just going to take this question off the screen, and then we can then proceed. So we've crossed over into security. Now we're looking at the different aspects of security. And if you're just joining us, we're looking at the triad of the security sphere: confidentiality, integrity, and availability. So at any given time, your data must be kept confidential. When your data is being transferred, it must be encrypted. When your data is transferred, to verify the integrity of the data, hashing algorithms are basically used. And availability then becomes important. But we just spoke about availability in the last. Right. We just spoke about availability in the last few slides. So we understand that it's pointless for you to secure the data, and in the process, it does not become available. So availability is a given in the fact that your data must be available. Now, we spoke about symmetric encryption, and we said you're using the same key. Asymmetric encryption is using two separate keys, right? They are known as a key pair. And you might have heard terms like public key, private key. And that is what I'm basically going to be explaining with public private key, how that basically works. To a certain extent, this is not fully in the syllabus, but it's important for you to know if you're going to be focusing on security, because this is the fundamentals of security. This is why you and I can go on our banking site and we can type our information and be partially confident that it's protected end to end, because the keys that are locking and unlocking are two separate keys. One key is private, one key is public. So you can distribute the public key so that anyone wants to communicate with you, they can use your public key to lock the data, and only the private key can be able to unlock it. That's why they're known as key pairs and they're running. So public key is basically a cryptographic key that can be distributed to the public and does not require secure storage. So it's a key that you can give out. As long as you keep in the private key, anyone can sign or encrypt using that key, and you can decrypt using the private key. And the private key is used by the recipient to decrypt the message. So the whole objective is we need to encrypt and unencrypt, encrypt and decrypt. That's what we're trying to achieve. So how do you transfer the keys? How do you move this information? And we enter the world of certificates, right? So we have certificates that we use on a day-to-day basis. When we're accessing sites, let me just try and see. Wait a minute. Okay, I'm gonna pull one of my screens so that I can demonstrate to you when we're saying certificates, what are we talking about and what are we referring to? Because I like things being practical. I don't like us to talk about things theoretically. Right, so let's go to google.com. Let me not distract you with all the other things that are on the screen. Google.com and press enter. Right, so if I come here, you'll notice that this connection is secured and there's a certificate that is being used. And this is the certificate that we're referring to. And in this certificate, we've got the SHA fingerprint, the SHA that we're talking about. So integrity perspective, they're using 256 for SHA. And then this certificate was issued on, let me just bring my pen, issued on the 15th of September. Let me just get the different color. 15th of September, and expires 5th of December. It was issued to google.com, and it was issued by Google Trust Services as the authority of that particular certificate. What else do we find out? If we come, just clear that. Right, if I were to come here, might not have, right, there's a serial number of the certificate. I'm just trying to see if I can get to the point. Yes, there's the public key. There's the public key. Right, so this is the public key of the Google certificate. So if I am talking to Google and information that I'm putting, they're encrypting this information using this public key. And when it traverses through the internet, that information is encrypted using this particular key. And then when it gets to the server is going to decrypt it using the private key. So this is the private key. This is the public key. So this is how public cryptography basically works. You got the private key, you got the public key, but we're going to go into detail. I just thought let us go and look at a real life example. If I go to Microsoft, let's go to Microsoft.com, every website that you go to, or maybe let me go, okay, Westpac. Okay, it's not my bank, so if you want to hack it, well, feel free. I don't bank with Westpac anyway. So if you go to Westpac, just erase that. Come here, you'll find that the connection is secure, and this is a valid certificate. Once again, this issue was issued to Westpac, and it was issued by Entrust Certification. So these are certification authorities that are available across the world that are able to issue out certificates. And we're going to be talking about that just now. I just thought we just look at a practical example. And once again, they have their public key that is available for all of us to see. And for all of us who want to use that or connect to that particular bank, we do have access to the public key. So when I start explaining, we're all clear on what a public key is and what is it that it basically does. So now let's come back to our conversation. So this happens in stages. And the first stage is step number 1. The PC makes a request for the server's certificate. So it's making a request for a certificate going towards the direction of the server. The server responds and sends the user the certificate. In the certificate are going to be the things that we covered. There's the common name, who the certificate belongs to. There's going to be the expiry date, when the certificate expires. And then there's going to be this key. There's going to be the public key. And what the public key is simply saying is that when that certificate is given to me, the server is saying for anything that you want to talk to me, encrypt using the public key, because I have a private key that is able to decode. So the certificate goes to the user. So step number 2. Step number 3, how does the user trust that certificate? How do I know that the certificate that I got came from a source that is genuine? That's where the certificate authority comes into play. So our systems have certificate authorities that they trust. And these certificate authorities are listed in our browsers on our PCs. It's just that I don't have the location to get to find it. But if you go and search online, you'll be able to find out that you can double check the certificates that are on your PC, and the ones that are basically, no, actually, let me check. I think I can remember vaguely. I want this to be as practical as possible, so we're just not talking theory. I can't share this part of my screen, but I'm just going to type this and I'm going to put that on the other screen so that we can see together what is taking place. Just bear with me. Okay, so we have erased. Let me erase that pen. Okay, what happened? Let's see. Okay, must have lost my pen somewhere along the lines, but let's go. So if I were to add my certificates and finish that, expand that. Okay, so you see this trusted root certificate authorities. If I open this, these are the root certificate or certificate authorities that my computer trusts. So if I receive a certificate, I then check who signed that certificate. If the certificate was signed by any of these trusted authorities, then I am going to trust that certificate. Why? Because I trust the person who signed the certificate. So let us take a step back and let's break down what it is that I'm talking about here. What I'm basically highlighting is you got a driver's license, right? Your driver's license is issued by your licensing authority. But when you get stopped by the police, when you produce that driver's license, they look at the license, they look at the authority who signed that license or who gave it that license to you. And because they trust the authority, they're going to trust the genuineness of that driver's license because they trust the authority that issued that particular license, even though they can't verify the license at any given moment. Same thing with the passport. When you fly from a country to a different country and you get to the airport, they've got no way to verify that the passport that you're carrying is genuine or not. But they trust that the authority that issued the passport is an authority that they trust. And because of that, they then trust your passport on that basis. So that's where the concept of certificate then basically come into play. Now, my screen seems to have stopped. My pen seems to have stopped working. Okay, it's back. Good. So we said, so the third step is when, all right, let's do that. So the PC extracts the public certificate and then it then encrypts all the traffic that it goes using this certificate. Okay, let's return that one step backwards. Good. So it's going to extract this public key. It's going to use this key to then to encrypt traffic. So it encrypts the traffic using this public key, and then the information goes through the internet encrypted. And then when it gets to the destination, the server then decrypts this using its private key. And then the information that is extracted, what came in here, is then received in the way that it is meant to be received. But remember, I said earlier on, asymmetric encryption algorithms are process intensive. You can't run this quite extensively. So where asymmetric algorithms are used is to share the key, the symmetric key. So you are just trying to make sure that as you communicate over the public interface, you protect the identity of the key and you use asymmetric encryptions to carry the key between the two sources. And then when the two sources now have a shared key that they can use, then they'll then default to symmetric encryption because it is much more faster, much more quicker, and it is less resource intensive. So the whole objective is to be able to then give you a shared key that you can use, because if you send it via email, someone could intercept it. If you send it via mail, someone could open the mail. So you're trying to protect that whole process, and you've got that done, and you can get that going. So most of the times, asymmetric encryptions are used to share the key, and after that, you're going to be running symmetric encryption algorithms to then handle your interaction. So I hope that makes sense. If you've got any questions, you know what to do. We are going to go to the next slide. So now we're looking at the different threats and vulnerabilities that we can encounter on our network and how we can protect against them. And when you're talking about threats, we are basically looking at the potential occurrence of anything that could cause harm on our asset. And when we're looking at vulnerabilities, we are looking at the weaknesses in our system. And as you can see the picture on the screen, once upon a time, there was something known as hot wiring. I'm saying once upon a time, I mean, it might work, but the cars nowadays probably are much more smarter than the cars back in the day. But I'm not a mechanic, so I say that with discretion. But the whole concept of hot wiring was the cars were vulnerable in the fact that you could start a car without a key. All you need to do is just to cut the wires and then join the wires and then bang. If you grew up watching MacGyver, then you would understand all this, because MacGyver was the guy who could be able to, spark a car and get it started. So cars in the olden days had a vulnerability, and the vulnerability was the fact that you could hotwire a car and start it without a key. So who exploited that? Thieves. Car thieves would break in, as long as they can break the window and get into the car, cut the wires, start the car, and then they can get the car going. But obviously, as technology advanced, now most of the car keys have a chip inside the key. And that chip, when you put your car in the ignition, when you put the key in the ignition, the coil has a pairing inside the car. And if you put the wrong key, the car is not going to start. I'm not so sure if wiring still works, but my point is they try to secure cars. So when you're talking about the vulnerability, we are saying what weakness does your network have? What weakness does your system have that can be compromised or exploited by people? And in the networking or security world, we have what is known as the CVE, which is the Common Vulnerability Exposure Database. And this is basically a database that showcases different vulnerabilities on different devices that you need to then patch. So usually when a vulnerability is identified on either a router, the vendor usually comes up with a patch which fixes that particular vulnerability. So what CVE does is that it publishes the vulnerabilities in different devices, and it becomes your responsibility to make sure that you patch your devices to protect against that vulnerability. Same thing with updates on Windows machines. You are basically trying to patch some vulnerabilities that have been identified and make your systems more secure. And if you're going to be dealing with the security space, CVE is something very important for you to be able to know and understand. So a threat is the potential, and you calculate threat using risk percentages, right? What are the likelihood of people hacking our system, right? Is it on a scale of 1 to 10? Is it 0? Is it 10? What data do we hold that people might want to steal from us? Vulnerability is your weakness. Exploitation is people exploiting that vulnerability. So on your defense side, your objective is to try and have as very few vulnerabilities that people can exploit so that you can be able to protect your network. Now, in this whole protection, yes, we can patch, but there are other things that we can do in order to protect our networks. And one of the most common ones is something known as least privilege. One of the most challenging aspects about organizations that get hacked is that there was this one super user account that had almost all the privileges. So when people gain access to that account, they basically gain the keys to the whole kingdom. Why? Because one account had multiple permissions. So with least privilege, the objective is try and give accounts the permissions of the things that they need to do and nothing else. So let's clear this. So I work in IT, in networks, and then I'm also an administrator to access network systems, and then maybe I also need to access databases. Least privilege simply says I should have one account for my daily use, I should have one account for the administration part, I should have one account for the database part. So if you compromise one of the accounts, the assumption being that the passwords are not the same, you don't have an ability to hop and get to the next account and then cause harm. But if all these privileges were on one account, it means that when you compromise that one account, you got the whole, and most of the hack, if you read most of the stories of hacking and organizations being hacked, a great percentage is related to the fact that the account that they got access to had multiple privileges. So in order to mitigate that, they always recommend that have accounts that have got minimum privileges so that you can be able to avoid finding yourself in this situation. The next step is something known as role-based. And role-based simply says, we are not going to define the permissions of an account based on an individual, but we're going to define them based on the role in question. So we're going to create a role and say, okay, fine. For an accountant, what does an accountant need, right? We need access to server 1. We need access to XYZ. We need access to XYZ. And then we give permissions to the role-based account. And then we add users into the group of that. So that way, you're not defining permissions based on individuals, but you're defining permissions based on the role in question. And it just helps you to mitigate this ability of giving individuals, because it's one of those, I come to you like, hey, I can't access this server. Oh, sorry. Okay, cool. Bang. Add my account to the group. Before I know it, I've got 10, 15 groups more than what I need. And I am putting the organization at risk. So these are some of the strategies that can then be used to be able to protect your network. Things like zero trust. Zero trust simply says, I'm not going to trust anything. So the best example I can give with zero trust is we tend to trust people in our organization because the assumption is that when someone is in the organization, they are trustworthy. General networks usually used to trust traffic that is inside of the network, right? Because you'll be like, okay, it's trusted networks. Sorry, trusted traffic. So most people would not segment their network. So what I'm basically referring to is this is the router that takes us to the internet. This is the inside of the network, right? So we've got this switch. We've got this switch. When you've got this switch. General networks, simple say the PC connected here could go all the way this way and talk to a PC connected here, because the assumption was that we are inside the network. This is inside and everyone else is trusted. But zero trust simply says, just because we're inside does not mean that I can trust you. I should put segmentation and say, for you to go to here, I need to put either an ACL or I need to put a firewall. And that firewall then queries to say, who are you? What do you want? Are you permitted to then go in there? That way, if this part of the network is compromised, the person who compromised does not have full reign on the entire network. Why? Because your network is segmented and it is protected. So zero trust simply says, I don't trust anything. I don't trust anyone. I'm going to implement security from a point of no trust. And I'm going to permit everything, whether you're inside or you're outside. And the next one is defense in depth. Now, this one is more exciting to me because most of us, you have your fence, right? So this is your outer fence. And then you have your security cameras that are placed in there. And then you've got a house inside. Your house has got windows, it's got doors, and those doors have got locks. So when you're implementing security, you don't say to yourself, just because I've got an electric fence and I've got cameras on the outside, I'm going to sleep with windows opened and the door unlocked. You're probably going to lock your door. You're going to close your windows. Why? Because you are having multi-layers of security. If you break the gate and the electrical fence, you have to deal with the cameras. If you deal with the cameras, you have to deal with the dogs. If you deal with the dogs, then you have to then break the window, break the door to get inside the house. It's multiple layers of security. And that's the same thing with our networks. We just call it defense in depth, meaning you have different layers of protection before someone can then get to the data that they're trying to. So you start with physical access. You probably have access cards to get into the building. Why? Because I want to protect people to get inside. And then when you get inside, I then implement 802.1x to stop you from just plugging onto the network port and being able to then get access to the network without being authenticated, right? So I'm protecting my network in multiple layers. And in the next slide, you're going to be looking at what options do you have when you're basically dealing with defense in depth, and how then do you then protect? So the first one is network segmentation. We spoke about it earlier on, and I said, just because it's internal to the network, you need to segment. We spoke about VLANs. The last time I said VLANs provide network segmentation. It could be one switch, but these ports could be one VLAN, and these other ports could be in another VLAN. and that is a layer 3 boundary. Ultimately, if you want to talk to PCs sitting here, you need to go here. Either there's an ACL or there's a firewall that is protecting traffic crossing over to the other side. That is network segmentation. Or you can segment your network and probably have a router or have a firewall. Some organizations have internal firewalls. So you've got a firewall that is sitting here that is separating different networks. And for you to cross over, you have to go to the firewall, and the firewall then says, what port do you want to access? What network do you want to access? What device do you want to access? Can I allow you? If you're not allowed, you're implicitly denied. And that way, that protects your network. Then we've got something known as DMZ. And this might be very familiar. If you have spoken to anyone in networking or read anything about networking, you have heard about the DMZ. Now, the DMZ, the dilemma that we had is, once upon a time, this is not probably prominent nowadays because of the cloud, but once upon a time, we used to have a web server that users who are coming from the internet need to access because it is carrying our website for the organization. And then also there was email, right? So users needed to access this information. But the challenge was, if we place this in our internal network, then we are risking other servers that are sitting on our network, because then when someone gets to these servers, they're able to get to our network. So they then came up with what is known as a DMZ. And what the DMZ basically does is, it is a semi-trusted network that is segmented from the rest of the network. So your organization, this will be the internal network, this will be the DMZ, and in the DMZ, you place servers that are public facing. So you then give people that are coming from the internet access to servers in the DMZ on specific port numbers, and then deny them the rest of the inside network. Or in some instances, you actually have two different IP address subnets. So just because this is reachable on 13.13.5.5, the rest of the network will be reachable on 14.5.5.0/24. So ultimately, because they're two separate networks, you are protecting the two. So the DMZ is like a separated network that is part of the organization, but is accessible to the outside world. It's like a gatehouse for a security guard. There's one window facing the outside of the yard, the other part is inside the yard, so that the security guard can sit in between and see what's happening on either ends. So that's where DMZ comes in, and that's how that basically functions. So remember, onion has got multiple layers. For you to get to the core of the onion, you have to peel it and peel it and peel it. And it's tedious to try and peel an onion to get to the core of it. And that's security and defense in depth. The more your network is multi-layered security-wise, the more difficult it is for someone to penetrate. But if you have you've got few layers, then it's easy for you to be able to penetrate. We spoke about least privilege, role-based account. Now we're looking at separation of duties. If I work as an administrator, I must not have access to change multiple systems, because most of the crimes, especially financial ones, it's when someone has got too many access rights as an individual, that they can go to the system to withdraw money, and they can go to the system to cover up the withdrawing of the money and be able to cover their foot tracks, because they've got multiple systems. So separation of duties is, no one person should have too much power to be able to commit the crime and cover up their foot tracks in the process. It must be a coordinated effort that I need someone else to do their part in order for me to then commit the crime. And that way you're adding multiple layers in your defense. You got network access control, which is 802.1x. I spoke about it earlier on. This is when we are protecting our switches, and we are saying that the port is not going to go active until someone authenticates. And after someone authenticates, the port opens. So if you can't authenticate, the port is going to remain shut down, and anyone who just plugs into any port, either in the reception or some part of the building, they can't get access to the network. And the last port is something known as a honeypot. And a honeypot is where you've got a dummy network, right, that you allow people who are trying to hack into your system to go to that network. To them, they think that they're actually hacking your system, but on your end, you're basically monitoring what they're doing and trying to see the sophisticated tools that they're using to try and compromise your network. So in some instances, you've got honeypots that basically redirect and allow you to just get visibility of what the bad guys are trying to do on your particular network. So these are the ways that you can defend. I mean, they're not the ultimate, but that's a very good starting point in being able to defend and protect our networks and make sure that they're basically secure. But whilst we can implement this, this is not enough. When I'm saying this is not enough is, remember, security is multi-tiered. There are things that we can do. There are things that we can do on an authentication side, right? So we just dealt with what you can do, least privilege, role-based. But from an authentication perspective, how do you protect your network? So once upon a time, we all used to depend on username and password. Username and password was all that we needed. And as long as you got the username and password, Bob is your uncle, you got access to the system. But username and passwords came to a point where they're not secure by themselves. Why? Because there's something known as man in the middle. And a man in the middle attack is someone who's intercepting traffic as it is going from one point to another. And because they're eavesdropping, they can see what is taking place. So they can get your username and they can get your password. That's one way. Number two, people are getting hacked. In Australia, one of the biggest telcos just got hacked and 2.whatever million records of people got lost in the process. In some instances, they hack and they get the username and password. So we have to have other tools to protect. And the first tool is something known as MFA. And I'm sure by now, MFA is now a very popular term. And MFA is basically multi-factor authentication. You just don't depend on username and password, but you need a third verification. And the third verification is probably your mobile phone. You got an app on your mobile phone. So when you log into your server, email server, bank, whatever, they ask you to provide another form of authentication, and then they send a PIN code. Sorry, they send a one-time PIN to your phone, which will have a code 513512. And then you put that code in here, the server verifies, and then your account is what? Is opened. If someone was to steal your username and password without the one-time PIN, they can't access your what? Your bank account. It's a multi-factor authentication. So just multi-factor options. It can be one-time PIN, it can be biometric. You know, you could use authentication services like Google Authenticator. There are multiple ways that are just allowing you to confirm that it is indeed you who's trying to log in. The one that I've encountered of late, PayPal does it. And I think StreamYard does the same thing, where you don't have a password in the system. Whenever you want to log in, they'll send you the code to log into either to your email or to your mobile phone. And I thought that was brilliant because I don't really keep a password in my mind. And then the next is TACACS. TACACS is the Cisco protocol for authentication, authorization, and accounting. So when you are connecting to Cisco devices, you want to be able to authenticate. Authentication is just verifying who you are and permitting you based on the credentials that you provided. And then authorization is based on the credentials that you provided, what commands can you type on a Cisco device? And then accounting is being able to then track everything that is taking place. And TACACS allows you to be able to then do that. That leads us to single sign-on. Single sign-on is something that is now probably common nowadays. In its simplicity, single sign-on is signing onto one system, but being able to access multiple systems out of that one single sign-on. Where have you seen this? There are some applications that when you connect, they say to you, do you want to use your Facebook account to connect to this application? And if you say yes, they will then go and authenticate you against the Facebook server and give you access to Twitter. And then maybe you do the same thing with YouTube. So what you're simply doing is single sign-on. You sign on once, but you sign on to multiple systems. At work, you might sign on to your PC, but in that, you automatically log into Outlook, you automatically log into SharePoint, and other systems that come along the line. So you don't have to multiply individually log into these devices one by one. And that way it protects you using your password multiple times. But at the same time, if you get compromised, someone has got full access. Radius, we spoke about 802.1x, and we said 802.1x is made out of 3 components. We've got the supplicant, who is the switch, and you said you got, sorry, who is the PC? We've got the authenticator, who is the switch, and then you've got the authentication server. And the communication between the authenticator and the authentication server, we said we use Radius. So Radius is a protocol that is used for carrying credential information between the authenticator and the authentication server. So it basically just protects that information or the credentials as they are traversing through. So by virtue of that, Radius encrypts that particular traffic as it basically goes through. So it uses UDP, and UDP operates on port 1812 and 1813. Those are the 2 ports for Radius to be able to then function. You can also use local authentication, and local authentication is basically you authenticating against a local database. You create a username and password on that particular device, and then you connect to that particular device. And then you can use 802.1x. So these are the ways that you can protect your authentication when you're configuring your network devices to make sure that your network is secure and you're not compromised. Now, here we're looking at risk management. We've got a lot of risk that we encounter on a day-to-day basis. On our networks, security-wise, we've got different risks. The risks that we have are risk of a threat. And when you're dealing with risk assessment, you're basically looking at the credibility of a threat happening. You're looking at the past. What might have happened? You're looking at the industry to say, other organizations that are similar to us, how many of them have encountered this particular threat? And what is the possibility that we are also going to be targeted? And if you look at most organizations that are being targeted by hackers, these are organizations that are intensive or hold a lot of user data. Why? Because user data is something that sells well. Identity theft is something that sells well on the black market, and there are people who are willing to steal your identity so that they can open credit cards and do financial transactions using your identity. So anything that holds identity. So if you're an organization that holds people's identity information, then the threat level is going to be higher compared to organizations that don't hold people's information. I don't remember anyone of the fast food outlets being hacked, because if you hack McDonald's, yeah, maybe you might get the secret, but can't steal any burgers. But organizations like Uber, who hold a lot of end user data, are ones that are basically targeted by most of these hacking organizations. So when you're dealing with risk management, you're analyzing threat assessments and just trying to work out how vulnerable are you to a threat and be able to mitigate in that direction. When you do a vulnerability assessment, you're basically looking at identifying, quantifying, and prioritizing your vulnerabilities. So you might have 50 vulnerabilities that you have, but you also can't fix all the 50 vulnerabilities. So you work on priority. If your house is leaking versus the grass has not been cut, clearly the leak in the house has got a higher priority than the grass that has not been cut. So you would focus on protecting the leak so that when the rainy season comes, your house does not collapse and you have structural issues, and then you can attend to the grass later. So it's the same thing. When you do a vulnerability assessment on your network, you're trying to say, these are my vulnerabilities, which ones can I remedy quick, fast, and what's the magnitude of the vulnerabilities? And I'll probably start attending to the ones that have the greatest magnitude or have the greatest impact if I then suffer a threat in that particular direction. So When you're looking at assessments, you're basically just doing a posture of our network and trying to see how do we protect ourselves. You can do penetration testing. That's an industry all by itself, very prominent industry. People are making money out of penetration testing. And its simplicity is you're giving someone permission to do a test on your network to make sure that it is secure. So if you're doing penetration testing for a house, I'll try and jump the fence, see if the electrical fence is working. I'll try and jump the fence to see if the alarm is working. I'll try and jump the fence to see if the cameras are functional. I'll try and see if the dog is doing whatever it's supposed to do and protecting you. And by doing all this, I'm trying to then prepare that in the event that I've got an ultimate threat, I am secured enough to be able to protect myself. Process assessment, you are basically looking at your processes. When someone joins the organization and they're given username and password, are they adhering to the limitations of the password and all the things here? So you're doing a process assessment to make sure that you are basically abiding to your security standards and security policy. And then vendor assessment basically looks at the vendors that you're working with in your organization. How much data do they have? I think if you research the Stuxnet, that happened in Iran, where the vendors were able to go into the organization carrying USBs that carried the malware that then attacked the nuclear plant. And that was the vendor coming through. So you need to do a vendor assessment. What vendors do we have when they come into the organization? Do they connect to our network? What access do they have? The account privileges and things along the lines. All these things are very, very, very important for you to then make assessment. And the last one is posture assessment. And posture assessment, you're basically looking at the device and you're simply saying to yourself, maybe you're running Windows 10, any version less than 10.3 is going to be denied on the network. So when you connect to the network then does a posture assessment of your operating system. And if your version is less than 10.3, then you're going to be blocked. You can't access the network until you have upgraded to 10.3 and above. And that is what you're using to be able to protect your networks. And we call that posture assessment. And we're probably going to close off for today by looking at, let me just see. By looking at the different types of attacks that we can encounter on our network. Right, how can you be attacked? I'm just going to write them down and I'll probably explain them later on. We have what is known as denial of service. Denial of service. And then we have a DDoS. I'll explain that. We've got men in the middle. We have DNS poisoning. And then we've got VLAN hopping. So these are some of the attacks that you're likely going to encounter and that you need to protect from a security perspective. The denial of service is basically your systems being flooded with so many requests that the system can't cope with responding. And in the process, services are basically denied because the servers have been overwhelmed by the amount of requests that are basically coming through. I think earlier on we spoke about TCP, and we said TCP uses something known as a three-way handshake. And one of the most common denial of service attacks is sending TCP SYN attack that overwhelms the server, that it does not have capacity to respond back. And in the process, it uses all its memory, bandwidth, and all the things that come along CPU. And then the normal servers that need access to the network are basically denied because it has been overwhelmed. When you talk about distributed denial of service, this is where you've got bots that are basically sitting in different locations and you're being pummeled from different side of the internet, basically attacking the same servers from multiple directions. And that's a distributed denial of service because it is spread across. And I think there's a documentary on Netflix that looked at when Julius Assange was arrested. There were some organizations that took offense. Security organizations took offense, and there's some hackers that attacked organizations such as MasterCard because I think they froze the accounts for, I don't know what is the name of the website that these guys were, not Wikipedia, but there was some website of some sort where all this information was being leaked. And I think they blocked payments to that, and people were not very happy, and they launched a denial of service on the MasterCard website, and it blocked it for quite a bit of time. You've got man in the middle. Man in the middle is you have network information traversing, and then someone is able to intercept traffic and be able to watch what is taking place. And because of that, they can eavesdrop, listen, get username and passwords. So many of the middle attacks are very common, and things like encryption are basically meant to protect that, because when you're encrypted, when someone watches the traffic going through, they can only see the gibberish, they can't see anything else, and they can't decrypt that information. So many of the middle attacks are very common. DNS poisoning is another important one. With DNS poisoning, remember we said DNS resolves host name to IP addresses. And what DNS poisoning does is that it redirects people to lookalike websites that might not be Facebook. They look like Facebook, but they're not Facebook. And then from there, you're going to put your username and password, and then they're going to harvest that information because they've redirected you to a fake website. I'll just check if there are any query. No, we'll probably finish off the last one. And then VLAN hopping is where someone connects to the network and they start hopping between different VLANs beyond what they're meant to have access. Because remember, VLAN is a virtual local area network. So this port might be in VLAN 10, this one might be in VLAN 40, and the VLAN 40 is the secret VLAN that we're trying to protect. So VLAN hopping means someone can get into VLAN 10 and then they hop through until they get to VLAN 40 that is protected. So we need to make sure that we stop that from happening and you're able to then mitigate. So that basically takes us to the end of what we wanted to cover today. We're probably going to continue with security. There are a few other items to then cover. And then we're going to go into troubleshooting. And probably sometime next week, by Thursday, we should probably close off and should have covered everything else. I'm probably going to do a video dedicated on just beyond the technical parts. What else do we need to know? So if you've got any questions, or if there's something that you feel like you want me to cover, please don't hesitate to let me know. I think I've got a question. I'm going to put it on the screen, and then I'm going to answer that. Okay, so what is the difference between explicit deny and implicit deny? That is a brilliant question, and I'm going to try and answer it. So explicit deny is where in your access list, you say to yourself, I want you to deny, this is the sequence number of the access list, deny IP any going to 8.8.8.8, which is, in our case, this is the Google server or Google DNS. So I'm denying anything going to the Google DNS. That is an explicit deny, because I am specifically saying I don't want any traffic going to the Google server. Implicit deny, on the other hand, is every access list has an implicit deny at the end, meaning I need to have at least one permit statement. So let's say I want to permit IP any going to 4.2.2.2. What I have simply said is anything going to 4.2.2.2 is accepted, but at the end of every access list, there is an implicit deny. I don't have to type anything. I don't have to write, I don't have to say deny any. No. At the bottom of every access list, there's a what? There's a deny. So because of that deny statement, that is an implicit deny. I don't type anything. It's there. So if you don't permit anything on an ACL, everything's going to be denied. Why? Because every access list has an implicit deny. So the best that I can give is, if you got kids, the first answer when they want candy is no. That's an implicit what? Deny. The explicit deny is when they come and say, I want candy, and I say no. I'm explicitly saying that no, but also there's an implicit deny that there's no candy that is supposed to be consumed in this house, because candy is what? Is bad for you. So that's the difference between implicit and explicit deny. That's a very good question. The next question is, these questions are becoming exciting. Yeah, maybe we'll probably have a time that's just dedicated for questions and questions alone. Let me just go to the next one. I think it was, okay, yeah, it's probably one and the same thing. Difference between explicit and implicit deny. So yeah, guys, this is, that brings us to the end of today's topic. I am looking forward to the next one, and I trust that you guys have a very good day. If you've got any questions, please don't hesitate. Send me an email. I just see someone has come back online at the moment. If you've got any questions, I'm here for the next minute. If not, then all is well. So Brett, I hope I've answered all your questions. If you still have any questions, please don't hesitate. Just send me an email. My email is somewhere in the description below. And for the first time, if you're interested in much of this content, don't hesitate to subscribe. Leave me a comment, but subscribe so that at least you can be updated. And I'm probably going to be saying that now. I'm currently working with someone to do a Security Plus bootcamp. So if you think Security Plus is something that is interesting, exciting to you, please let me know in the comments and let us see what else we can basically be able to cover. If you think that there's any course that you feel it is crucial for you that you want us to cover, just let me know. But other than that, thank you very much for taking your time. I'll see you in the next one.